In this screencast, we're going to take a look at how energy is unleashed from atoms. Recall that the nucleus of an atom is composed of two subatomic particles, the protons and the neutrons. Atoms of the same element that have different numbers of neutrons are called isotopes. And so these isotopes are going to be radioactive, and that is what we're going to be seeing when we're dealing with nuclear reactions of fusion and fission. The term fusion comes from the Latin word fuse, which means to melt. It occurs with high temperature and pressure, and where lighter nuclei combine to form a larger nucleus. It takes place naturally in the sun and the stars, and needs temperatures of over 10 million degrees Celsius to occur. In fusion, an isotope of hydrogen with one neutron is called deuterium, or heavy hydrogen, and it has, it's called H2. Okay, so it has the atomic notation of H2, and here we see an image of that. And then we also have tritium, which is going to have two neutrons and a proton. And when they fuse together, okay, so when these two atoms collide with each other, what happens is they form a helium nucleus and they give off an energetic neutron. And that's where we get our energy from. Fusion does not produce radioactive waste, okay? So, where does the massive amount of energy from nuclear reaction come from in fusion? Well, imagine weighing the separated protons and neutrons before they smash together, and then weighing them after they smash together to form the new nucleus. The separated particles weigh more than the resulting nucleus, and the difference in the mass is called the mass defect. The difference in mass becomes the amount of energy produced during fusion if we use Einstein's famous equation, E equals mc squared. So what is nuclear fission and how does it happen? Well, fission comes from the Latin stem word fis and means to split. In essence, what is happening is we're releasing the energy of an atom by breaking a large unstable nucleus into smaller nuclei and particles. And this is the process that takes place in nuclear power plants and in atomic bombs. The amount of energy released is staggering. A baseball-sized amount of enriched uranium has the same energy production potential of 1 million gallons of gasoline. But one problem is that fission produces radioactive waste. So where does the massive amounts of energy from the nuclear fission come from? Well, the mass defect can be converted into energy using Einstein's equation E equals mc squared. And this is called the binding energy of the nucleus, and it's sort of like a nuclear glue. So imagine removing the nuclear glue from a giant uranium-235 atom and from the nuclei of the products of the fission reaction of uranium-235, which would be barium-141 and krypton-92. There's more glue in the uranium-235 nucleus than there is glue in all of the products of the fission. So if we convert the mass of the nuclear glue into energy using E equals mc squared, then that's the amount of energy that's being released when the giant atoms split during fission. So here we see a comparison of fission and fusion, and recall that fusion is where we're taking the two small nuclei, so the deuterium and the tritium, we're smashing them together and we're making a helium atom and releasing energy in the process. And remember that the energy is being released because of the mass defect, because the mass of the particles when they're separate is different from the mass when they're together. On the other hand, we see fission, which is where we're taking a large atom and we're splitting it into smaller atoms. Recall that the energy from this comes from the fact that the binding energy, or that nuclear glue, is different between the products of barium and krypton and what we're starting with, the uranium. And so that difference in the glue that holds it all together, that energy is what we see with the fission reaction where we have nuclear power or nuclear bombs. To witness a nuclear chain reaction, I'd like for you to watch the video clip that's located in Schoology. In the video clip, you're going to want to watch from 48 seconds to 4 minutes and 6 seconds. And you want to make sure that you're taking note of the information that's in this table. So jot the table down in your notes and make sure you're comparing the critical process with the supercritical process in terms of number of dominoes, the reaction time, and the dominoes per second.